Another consequence of the method of linear approximations is Newton's method. Newton's method is the answer to a problem which is fairly general, fairly common in mathematics, and the problem is the following. Let's say that you want to solve an equation of the type f of x equals 0. So we have an equation. This is fairly general because anytime we have an equation I can move everything to the left, and so we have some expression of x on the left hand side equals 0. But now let's assume that the equation is not easy to solve. Okay, so we know how to solve certain basic, fairly simple equations, but there are other equations which are not easy to solve, and so there is no algebraic method to get them. Okay, so what we're going to do is we're going to apply a compromise. Okay, we can't get the exact solution. There is no algebraic method which gives us the exact solution. We're going to get a good approximation instead. Now, there are some basic but fairly rough methods to get an approximation. In fact, there are methods that give us an approximation as good as we want, but again, they tend to be not very efficient. So what we're going to do instead is we're going to construct or build up another method which is going to be a little bit more efficient. And the way we're going to do it is we're going to use tangent lines to linearize our curve. Okay. Notice, by the way, that what we're looking for is the intercept of the function f of x. Right? I didn't mention it before because I thought that you probably already noticed that on your own. But if you haven't, well, look it up. Right? If we're looking at for the solution of f of x equals 0, we're looking for the intercept, the x-intercepts of f of x. So what we're going to do is we're going to try and use linearizations of our curve to try and get a better estimate of this intercept. Let's see how that is done. Now, the idea of Newton's method geometrically is should be fairly simple. What we do is we say, all right, we're going to start from a good guess. So let's say that I pick a point which I think is pretty close to my intercept, and I say, all right, is that the intercept? No, we're not on the x-axis. We're a little bit off the x-axis. All right, so what we're going to do next is we're going to construct the tangent line at that point, which is not our intercept, but it's our first guess, right? And then what we're going to do is we're going to use this tangent line to get the next approximation. Notice that because the tangent line is going to run fairly close to the curve itself, it's going to hit the axis fairly close to the x-intercept that we're looking for. Okay? So what we're going to do is we're going to get this tangent line to get a better guess. Notice now we have moved our guess to this second point. Well, we're still not where we should be, but we are already closer. Okay? So what we're going to do is we're going to do it again. So we're going to draw the tangent line or construct the tangent line in the new point, and we're going to construct a new approximation to the intersect. Now notice, even from the picture, even after just 2 iterations of this process, you can't tell whether that green dot that we found is the real intercept we're looking for or it's still an approximation. Turns out it's still an approximation. But again, it's very good, isn't it? And if we're not happy with it, well, keep going. Just do more approximations and keep going with these approximations until you're happy with it. Well, this is the basic idea behind Newton's method. If you're not too sure, well, just rewind and watch it again, and until you understand how the method works. And I'm going to show you also how it works algebraically. One thing that I want to add is that this method is often referred to as the Newton-Raphson's method. Raphson is another mathematician who actually contributed to the method, and so his name is sometimes attached to it. There is an interesting story behind that. I'll let you figure it out on your own by Googling. So let's have a look now at how this method works algebraically. So here is the algebraic version of the same method. Remember, what are we going to do? We're going to start from an initial guess, which we're going to call x0. That's our starting point. It's not even a guess, it's really a wild guess. Okay? But of course, you want to make that guess as good as possible to begin on the right footing. So what we do is we figure out where the function is at x0. That gives us a point. Now we're going to construct the tangent line. Well, we know how to construct the formula for the tangent line. Since we know f prime of x0, or we assume that we know or that we can figure it out, we can construct the equation of the tangent line. It's going to look like that. I'm going to call this n1 of x because it's the first tangent line obtained through Newton's method. Now what are we after again? We're after the x-intercept. Well, it's easy to get the x-intercept of the tangent line. All I have to do is set the y-coordinate equal to 0 and then solve for x. And I'll ask you, maybe it's a good idea at this point to pause and make sure that you can, on your own, figure out that the solution of that equation is given by the formula you see right now on the screen. and I'm labeling this new guess as x1. So that's my first estimate. The first one was sort of a wild guess. This one is the first systematic estimate. Okay. Now, are we where we want to be? Well, not yet. You can tell that's not really the intercept of the curve. It's the intercept of the tangent line. So what we're going to do is we're going to repeat the same process. So we're going to now start from our new initial guess, x1. And again, we're going to construct the tangent line. And again, we know how to construct it. Oh, too fast. We know how to construct it. Okay. Now notice that this equation you have in front of you is exactly the same as before, except for the fact that we're using x1, I mean, instead of x0. That's not surprising. We're using exactly the same method. Okay. And therefore, when we find its x-intercept, well, we're going to do exactly the same thing. Set the y-coordinate equal to 0 and solve for x. Well, does that look familiar? Okay, well, that is exactly the same formula, except that now we're using x1 to get the next estimate, which is x2. Now, if we're not happy with it, we may be happy. It looks, again, graphically that we're okay. But if we're not happy with it, we can repeat it. And I invite you to do it one more time and realize that the formula you're going to get is exactly the same. Namely, every time you apply this method, you get a new estimate, which is given by this formula. Old estimate, which is this one, xn, minus the ratio between the value of the function at the old estimate divided by the value of the derivative at the old estimate. Okay? So what we can do is we can use this formula repeatedly until we're happy with it. Okay? So because of the fact that this method requires the repetitive use of that formula, it means that it's ideal for a computer. Okay? Does it work always? No, it doesn't. Okay? But it works reasonably well if the initial guess is close enough to the actual solution. So if we start on the right track, if we pick an x0 which is close enough to the intercept that we're looking for, then probably it's going to work well. Also, it works reasonably well as long as the concavity does not change wildly. Okay, so we want a curve which is a quiet curve. Okay, so it curves but not that much. Okay, so if the concavity really goes wild, then we may have a problem. There are other strange phenomena that may happen. Okay, but again, we're not going to go too much in depth in analyzing what kind of phenomena make Newton's method go awry. But just be aware of the fact that that they exist. So therefore, use this method with caution, but use it. Okay, it is a useful method, so it's something that you want to take into account. Although, as we're going to see in class, it's becoming a bit of an obsolete method. But again, you'll have to come to class to have a discussion about why. So, see you soon.